Assalamualaikum and hello everyone. In this session, we're going to look at a new chapter, chapter 8, which is ordinary differential equation, or known as ODE. So, basically from this topic, the most important thing is that from here, we can know that by using the method to solve ODE problems, for example, if we want to analyze the response output of a differential equation system when initial condition input is applied. For example, if let's say we have a vibration system and if I apply 5 meter per second the velocity, so the spring will start, the mass will start to vibrate, and we want to know after a certain time, for example after 5 seconds, what would happen to the system. So for this chapter, we're going to look at ODE in engineering and some method to solve ODE problem, such as from Taylor series. You can solve using Eulers method or Taylor's method. And then in the next session, we're going to look at Runge-Kutta, whereby we have it is actually to solve second order problems by using improved Euler, hewn and modified Euler. And to solve fourth order problems, we can use classical and Runge-Kutta method. So what is ODE and its application in engineering? As I mentioned earlier in the class, in vibration, you are already aware what is free vibration and forced vibration, whereby for free vibration there is no external force, and for forced vibration we have external force. So the equation of motion for each system is given here, whereby for free vibration, since there is no external force, so it will be mx double dot plus cx dot plus kx equals to 0. And for forced vibration, we have force at the end. So, as I mentioned, for ordinary differential equation, if we give an input, for example, for this system, if I give an input of V0, let's say V0 is 5 meter per second. Okay, so what will happen to this mass as I applied 5 meter per second? Okay, the displacement of the body, for example, have this kind of response. And if I plot the velocity against time, v against time, as we applied an input or initial condition of 5 meter per second. So if I plot the velocity, okay, this is the response. As I mentioned in ODE, if let's say we put a certain initial value, we can find the output. For example, if I want to look at t equals to 3 seconds, or maybe here t equals to 6 seconds, so I can solve that by using either Euler's method or Taylor's method. So what is Euler's method and what is Taylor's method? In Taylor series, if you can still remember in the earlier chapter, it is given by this equation, whereby y of a function, y at the next iteration xi plus 1 is equals to yxi plus hy prime xi plus h squared over 2 factorial y double prime and so on. So for Euler's method, we only consider up until the first order, whereby yxi, so if we want to find y at the next iteration, is equals to y at the current iteration plus h y prime xi, whereby h, if you can still remember, it is a step size, and y prime is the derivation of the function itself. However, for Taylor's method, we normally consider up until the second order, whereby you have this term as an extension from the Euler's method. I hope from here you can see clearly. For Euler's method, it will be up until here only, and if we want to use Taylor's method, it will be extended until this term. So, in the example that I shown you before, because it is related to velocity v, so we change from y to v. Okay, in the previous one we can see y, because now we are trying to solve velocity. So we change the term to vti plus 1 is equals to vti plus hv prime ti. Okay, it's just a matter of changing to suit the problems. You just change the term from y to v. If you are solving, for example, you are solving about flow rate, okay, then you need to change from v to q. So it's still the same. Okay, we are only considering up until the first order, and if you're using Taylor's method, it will be second order. However, if we want to use Taylor's method, especially to solve v, okay, if you see for Euler's method, it is up until the first order v prime. So we know that v prime is acceleration. But if we want to use Taylor's method, okay, because we need to consider up until the second order, we will have the term v double prime, whereby we know that v double prime does not exist. So you must be careful when you use Taylor's method. Even though we are solving up until the second order, but when we are dealing with velocity, we know that v double prime does not exist. Thus, the highest order is v prime, which is acceleration. That means if you are using Taylor's method to solve velocity, example, if you're using Taylor's method, then it will be up until the first order only. Unless if you are solving distance, for example, I'm very sorry. I think yeah. Alright, so by now you have already understand about Euler's method and Taylor's method. So as I mentioned earlier, it is from the Taylor series. For Euler's method, it is first order, up until first order the term, and for Taylor's method, up until second order. Okay, so let's look at some example. A system y depends on another variable x following a differential equation. Okay, look, now it gives us the differential equation of 2y prime plus 3y is equals to e to the power of 2x. So we need to find the y. Okay, we need to find y, so meaning that this is the output when x equals to 1. So we want to know what is the value of y when x equals to 1. And the initial condition is given at x equals to 0 and y equals to 1. So this is the input. Okay, So if the input, we put x equals to 0, y equals to 1. So we want to know what is the value of y when x equals to 1. We can use Euler's method with the increment h equals to 0.2. So this is the step size. So we know that we need to use Euler's method to solve the problem of this ODE. So to use Euler's method, it's very simple, right? So if I can simplify the step, first, what you need to do is you need to write Euler's equation, whereby we know that Euler's equation from the Taylor series is up until the first order. So the equation is y xi plus 1 is equals to y xi plus h y prime xi. Second thing is you need to prepare the table, and then you just complete the table, right? It's very simple. So let's solve this example. So Euler's method. Okay, from example 8-1. So we've been given that the differential equation of 2y prime plus 3y is equals to e to the power of 2x. So we need to find y when x equals to 1, and given that the initial condition x equals to 0 and y equals to 1. So we need to use Euler's method, and the step size is given as h equals to 0.2. So from this information, okay, straight away we can know how many iterations that we need to do, because we start with x equals to 0. So if I plot, okay, so this is, for example, this is x. So we start from 0 and we want to finish at 1, and we know that the step size is 0.2. So 0.2, 0.2, 0.2, 0.2. So this would be 0.2, 0.4, 0.6, 0.8. So this would be the first, the 0 iteration. This will be the first iteration, second iteration, third iteration, fourth iteration, and fifth iteration. Alright, so from the h equals to 0.2 and from the information of initial condition and of the output, so we can know straight away that it requires about 5 iterations. So as I mentioned, that the step to solve Euler's method is first we need to write Euler equation. So the equation is y xi plus 1 is equals to y xi plus h y prime xi. Second, we need to prepare the table. So the table will consist of I, which is the iteration, and then x value, and then y, the y value, and then because from here we know that we need to use hy prime to find the next iteration, so this one would become y prime, and this is hy prime. So it's very simple. These are the only information that you need to write in the table, and as I mentioned, as I plot just now, in terms of the number of iteration, so fill up whatever information that we already know. So I will become from 0, 1, 2, 3, 4, and 5. Okay, 0, 1, 2, 3, 4, 5 for a step size of 0.2 to cover from 0 to 1. And the x value is given input as 0. So x is starting from 0. So with a step size h of 0.2, then they become 0.2, 0.4, 0.6, 0.8, and 1. And next, we know that the initial value of y is equals to 1. So y is equals to 1. So this is the only information that we know so far. So in the end, what we want to find is we want to find y when x equals to 1. Meaning that when x equals to 1, this is the value that we need to determine. So in order to determine that, we can use Euler's method, okay, and we can find this problem. Meaning that to find the value here, we just use this equation. But in order to use this equation, we need to know what is the value of hy prime. So first thing, before we find hy prime, we need to know what is y prime. Value here. And from the equation given from the question, 2y prime is equals to 3y is equals to 2y prime plus 3y is equals to e to the power of 2x. So if I write back that equation, 2y prime plus 3y is equals to e to the power of 2x. So now, from there we know that y prime is equals to e to the power of 2x minus 3y over 2. Okay, because we need to determine y prime. So we need to make y prime to be the subject. And then after you already determine the value of y prime, multiply with the h value and you can get hy prime. Alright, next step is we need to put all the values that we know in the calculator. So to make your life simple, in your calculator, so we'll use this x as x value, y we will use the term y in the calculator. So y prime, I'll change this to a in your calculator. So hy prime you can multiply straight away. So in order to solve our table, to complete our table, we need to do it row by row. Column by column and then row by row. Alright, first we determine y prime. So to know y prime is equals to e to the power of 2x minus 3y over 2. So you can input this equation in your calculator. Okay, so you can write it as e to the power of 2x minus 3y over 2. So make sure you put bracket first, okay, in your calculator. So when I input the value, so meaning that the x value, we take it from here, which is 0, and the y value is being given as 1 here. So using our calculator, the value that we will get is negative 1. So hy prime is 0, because we know that h is 0.2 multiplied by our y prime value, which is negative 1. Okay, we get it from here. So we will get negative 0.2. So now we have already complete the first row. And then moving on, we need to complete this side. As I mentioned, we can use Euler's method. So y at the next iteration is equals to yxi plus hy prime. Okay. Maybe I can use the term b here to make it easier. So you can input in your calculator. Okay. So in your calculator, okay, in order to find the y at the next iteration is actually equals to y plus b. Okay, so the value of y, so if I put y plus b, okay, our y value is from here, which is 1. So 1 plus our b value is negative 0.2. So the answer is 0.8. Okay, so now next we just need to complete our table. Then we complete the value here. So how to complete the value here? We can recall back the function that we have input in our calculator. So now the x value is not 0 anymore. It has changed to 0.2. Okay. And the y value is now 0.8. So if I input all the information in my calculator, I will get negative 0.4541. So hy prime is 0.2 multiplied by this value. I will get negative 0.0908. Okay, so now let's move on the third row. Okay, we need to solve this. So y plus b, again, our y value has now changed to 0.8. So 0.8 plus our b value now has been changed to negative 0.0908. Okay, so if I solve this, the value now is 0.7092. Alright, so next, put back all the values of x and y from this third row. Okay, input all the values, and we get the y prime is equals to 0.0490. So fast forward, after I put all the values in my calculator, so this is the value that I get, 0.7190, 0.5816, 0.1163, 0.8353, 1.2236, 0.2447 1.0800. So when x equals to 1, our y value is 1.0800. So this is how we solve the differential equation using Euler's method. So that's all for the session. Thank you very much and hope to see you again. Thank you.